Hello, hello, we're back better than ever. And tonight we're going to dive into relative extrema, which is basically kind of an umbrella title for relative maximums and relative minimums. And so tonight our major goals are going to be to determine on which intervals f of x is increasing versus decreasing. And we're going to mostly do that algebraically today. So for instance, f's increasing from this point all the way until here, and then starting here we're decreasing, 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 and then increasing all the way to here, and then decreasing from there to there. The other major theme tonight is to find the exact locations of all of our relative maximums and minimums. And so we've got, and a little side note, we're going to save these absolute mins and absolute maxes for tomorrow night. But tonight, our relative max here, you'll notice f changed from increasing to decreasing. Then we've got a relative min here where f changed from decreasing to increasing, and then another relative max up here. So a function can have a lot of different relative maxes spread throughout the function. Okay, just to make sure we've got a good feel for increasing and decreasing, we're going to play around a little bit here. And let's just draw kind of a random function here in our notebook. And we'll name this random function f of x. And we want to talk about, first of all, when is this random function increasing? Well, I would say, starting at negative infinity all the way up until this point right here, we would say f's increasing. Now what you'll notice at any point, and technically there's an infinite number of points along the curve within this interval, and if I tried to draw a tangent line at any one of these points, they would all have something in common. The slope at each one of these points is positive, okay? And whenever we say that the slope is positive, what we're really saying is that the first derivative is positive, and algebraically we'll just say greater than 0. So the first derivative is positive at each of these points here, every point on that curve. And then the same could be said starting here and all the way up until this point on the curve. Again, in theory, there's an infinite number of points between that relative min and relative max, and if I tried to draw a tangent line at any one of these points, the slope would definitely be positive again. So we're saying f prime, the first derivative, is greater than 0. All right. Now the opposite of that is true. We'd say f's decreasing from here all the way down to here, as well as from here all the way to x equals infinity. And again, if we just picked any random point along the curve, it could be here, it could be here, it could be here. What you'll notice now is that all of these tangent lines share something in common as well. The one thing that they all have in common is that their slopes are now negative. And when we say that the slope is negative, what we're really saying is that the first derivative, f prime, is now less than 0. So we've got f prime being less than 0. And so we really want to focus on drawing this connection between, okay, if I know f's increasing, what do I now know to be true about f prime? Or I could spin that around and say, well, if I knew that f prime was positive, what do I now know to be true about f? So we'll see if we can kind of put into words and generalize the things we just tried to hit on. So we say, if I know f's increasing, that implies, and that's what I like about this double arrow, it kind of says if then, we know that f prime of x, aka the first derivative, is got to be positive. Or like we wrote on the last slide, we'd say f prime is greater than 0. Or the converse of that statement is true as well. So I could say, if I know that f prime is positive, then that implies that f of x is increasing, for sure. Okay. All right. Let's see. If I knew that f was decreasing, what does that imply? That implies that f prime, the first derivative, is negative. Okay. Or as we wrote it on the last slide, f prime is less than 0. And again, the converse of that is true, and the converse here is the part that we're going to use more times than not. If f prime, let's see, let me erase that a little bit. All right, if f prime is negative, then I know that f of x must be decreasing, for sure. We're going to bear down here in the next couple of minutes and grind out some definitions, and we're really going to focus on the definitions. And some of this notation is real goofy, and you're like, why do we got to make it that confusing? It's not that hard, and we certainly don't want to make things harder than they are. But certainly the direction of the new College Board and AP format here is they're going to move more in the direction of theory, and so we want to really be good with our definitions, and I think that's going to contribute to our understanding of the theory behind some of these elements in calculus. But we would say that, first of all, our definition for a critical point. What is a critical point? Well, it's any point, we'll call that x equals c, in the interior of the domain of a function at which either the first derivative equals 0, okay, aka the slope is 0, or the first derivative does not exist. Okay? If either one of these two things is true, then we'd say there's a critical point at C. Now, so you'll notice right here at this relative max, you notice how the graph's very sharp right there and it's very pointed? Well, at that sharp point, I would say the first derivative doesn't exist right here. However, down here, here's another critical point, and I would say the first derivative equals 0 because of the tangent line having a slope of 0. And then up here, there's another critical point, and I would say the first derivative is equal to 0 again. Now, ironically, there's two other critical points. There's one hiding right here, and there's one hiding right here. And again, the first derivative is 0, first derivative is 0. And so there would be a grand total of 1, 2, 3, 4, 5 critical points on that domain. Okay, now what is a relative extrema? And we're going to break it into two subcategories here. Let C be any number in the interior point of the domain of the function. Then f of c is and we're going to start with a relative maximum value. So we can say there's a relative maximum value at c if and only if what? What has to be true? If f of c is greater than every other f of x for all x in some open interval. Now again, that is the craziest mouthful you've probably seen in a while, and let's see if we can dissect that a little bit. So when we say on some open interval containing C, what we're really basically saying is within this neighborhood, okay? So I'm not looking at the whole picture anymore. I'm just kind of restricting myself to a small neighborhood. And within this neighborhood or within this open interval, okay, there's a point C such that f of C is greater than every other f of x within that interval, okay? Same could be set up here. Within this neighborhood or within this open interval, there's a point we'll call it C, or in this case it's actually called D to be more specific, that f of D is greater than every other f of x within that neighborhood. So because we're only focusing on such a small neighborhood, that's why we said earlier that there could be multiple relative maximums and minimums on a particular function. Okay. Now the second definition piggybacks on the last one, and it's very, very similar. So we say there's a relative minimum value at C if and only if f of C is less than all the other f of x's within some open interval. So again, let's see, we've got this neighborhood, okay, here's a small open interval, and within this open interval, there is a point C, literally called C in the picture, such that f of c is less than every other f of x within that neighborhood. Okay, now we're really starting to gain some momentum. We're building up to the big part of the lesson tonight, and here's our first derivative test. And we're going to use the first derivative test to find where the relative maximums and minimums are. And so our definition here is f's going to have a relative maximum at point C if f prime, okay, make sure you're paying attention, this is f prime right here, changes from positive to negative. All right, and what's powerful about that, as we said earlier, what we're really saying is if f prime changes from positive to negative, we're really saying that f changed from increasing to what? Yeah, decreasing. Okay, second point here, we would say f's got a relative minimum at c if f prime does what? What's that first derivative got to do? He's got to change from negative to positive. And if the first derivative does that, then what we're really saying is that f changed from decreasing to increasing. Alright, we're going to dive in and do our first live example here, and there's really three parts to this problem. We want to focus on finding all critical points, okay? And just to recap our definition from earlier, that's either the first derivative equals 0 or the first derivative doesn't exist, okay? Second part, we want to figure out when f's increasing and decreasing, and third part, we're going to find all the relative maxes and mins. So, first things first, I am going to find the derivative of this function, which one of the friendlier derivatives we've seen in the past 2 weeks. So we got 3x squared minus 3x. Now the good news is this derivative will never be undefined because, quite simply, this is a polynomial, and all polynomials by definition are guaranteed to be continuous and defined for all values. The only time this undefined part really becomes an issue is if your first derivative right here is a fraction and then you grab this denominator and set it equal to 0, but that's certainly not the issue. So what I'm going to do now is just set this function equal to 0. Our algebra skills are going to take over. We'll take out a GCF of 3x. From there we can simply tee it up. We could say when x equals 0 and when x equals 1, those are my two critical points. First one at x equals 0 and second one at x equals 1. Now from here, to answer both parts B and part C, I'm going to construct what I call a number line, or sign chart I should say, sign chart. And let's see, on this sign chart, and I'm very particular about our sign charts, I want them to be very crisp and clean. We're going to put all of our critical points on the sign chart, and we're going to find the value of f prime over each interval. Alright, so my first interval is from negative infinity to 0. I'm going to pick any random number within this interval, and then I'm going to substitute it back into my first derivative. So I'm going to pick, we'll say, negative 1 as a test point. And you could plug it in here, but I like to plug it into the factored version, and a couple of reasons that we'll see over time. And when I plug in a negative 1, let's see, the 3x is negative, and the x minus 1 is negative, and if I multiply a negative times a negative, I'll end up with a positive value. So what I'm really saying is that for every value of x between negative infinity and 0, I know that the value of the first derivative is positive. Now what does that tell me about the behavior of f? That tells me that f's increasing over that entire interval. Alright, next interval. I can pick any number between 0 and 1. Probably the friendliest number in there is like a positive 1/2. And let's see, if I plug in a positive 1/2, let's see, I get a positive here and a negative there, and a positive times a negative is going to be negative. What does that tell me about the behavior of f? I now know that f is decreasing. So basically, everything on the top of the sign chart is describing the positive or negative nature of f prime, and everything on the bottom of my sign chart is describing whether f's increasing or decreasing. Alright, next interval. I can pick any number between 1 and infinity. Probably the nicest number in there is a 2. And let's see, 3 times 2 is positive, 2 minus 1 is positive, a positive times a positive is positive. And that tells me that f's increasing. So here's how I would answer part B. Alright, I would say f is increasing from negative infinity to 0 and from 1 to infinity because f prime is positive. And f's decreasing from 0 to 1 because f prime is negative. So that's the type of justification we'd be looking for on any quiz, test, spiral that we take throughout the year. Alright, next one. And again, we're really focusing on our justification here to make sure we earn full credit. C. I would say f has a relative maximum at x equals 0. Why 0? Well, because what's happening is we're going from positive to what? Negative. And that's exactly what I'm going to write. It's because f prime changed from positive to negative. Let's see if we can squeeze it in here. Alright. And then we could also say and you can still see the sign chart in your notebook hopefully here, f has a relative min at x equals 1. And why is that? Well, that's because this time f prime changed from negative to positive. Boom, there it is. Alright, here's a new interesting function, and our goal is to try to find all relative maxes and minimums. And in order to find those maxes and minimums, we're going to use what's called the first derivative test for maxes and mins. Alright, and because there is a trig function involved, I want to give you kind of a restricted domain, and so let's just keep it really simple and go from 0 to 2 pi, kind of our normal comfort zone there. And so the first derivative test says, first things first, I got to find the first derivative of f. So I got 1/2 minus the cosine of x. The good news is that both of these terms are always continuous in their own right, so the combination of the two together, f prime is always continuous and therefore always exists. So the only thing I've got to worry about is setting the function equal to 0. And when does cosine of x equal 1/2? Well, there's two solutions to that. One is 60 degrees, aka pi over 3. And then in the fourth quadrant, we could say x equals 5 pi over 3. Which was 300 degrees, 5 times bigger than pi over 6. Alright, from here I'm going to use these critical points to construct a sign chart. Now in this type, my sign chart is going to have clearly defined endpoints of 0 and 2 pi, as opposed to just throwing arrows on it, implying that it goes to infinity. So we've got pi over 3 right here. We've got 5 pi over 3. And I'm going to show you how to cheat a little bit, just because there is a trig function involved which allows us to cheat just a smidge. So within this first interval right here, between 0 and pi over 3, the friendliest value that I like to work with is 30 degrees or pi over 6. And when I plug that in, I'm going to plug it right into my derivative right here, and I'll show my work on the side. So I got 1/2 minus the cosine of pi over 6. 1/2 minus radical 3 over 2. And I want to say radical 3 over 2 is like 0.866. So if I did 1/2 minus 0.866-ish, now I'm definitely getting a negative number. And that's for f prime. So that tells me that f is decreasing. Now I should be testing, maybe I would pick, maybe like pi to test the second interval, or maybe I would pick 11 pi over 6 to test the third interval. Well, what's nice about trig functions is that we're guaranteed to change signs over each interval. Whereas if I was working with polynomials, that wouldn't necessarily be a guarantee. So I'm going to just cheat a little bit and throw in positives here, negatives here, meaning, f's increasing on that interval and decreasing on that interval. So to put the finishing touch on it all, we could say f has, let's see, I'll start with my relative maxes. Where is my relative max? At this guy right here. X equals 5 pi over 3. Because, why? F prime changed from positive to negative. Alright. And then we could say, well, by golly, f has a relative min at x equals pi over 3, because f prime changed from negative to positive. Alright, cool beans. Let me show you one more curveball. Alright, this particular function, we've got x squared minus 4 raised to the 2/3 power, is a very, very interesting function. And if you're really curious, try graphing it on your calculator, and I think a normal viewing window shows you a really wild picture. It basically, in a nutshell, when this exponent right here falls between 0 and 1, which 2/3 fits that description, some really wild things happen, specifically with relation to a cusp. Alright, now what is a cusp? A cusp is basically a sharp point. And so if I had to find the relative maxes and mins, I would start by calculating the first derivative. So I got my chain rule here. X squared minus 4 is my inner function. Now it's raised to the negative 1/3 power, and I'd multiply by 2x. Almost forgot my x. And just for fun, I'm going to clean this up a little bit, and I've got 4x for my numerator, and I've got a coefficient of 3 times the cubed root of x squared minus 4 on the bottom. And so we're trying to find all my critical points. And if I set my derivative equal to 0 like I normally do, cross multiply, and I would just end up getting x equals 0. But I also have to entertain the thought of, will this first derivative ever be undefined? And this is the first time tonight that we've had a derivative with a denominator that we had to worry about here. Alright, and so now what I'm going to do is I'm going to set that equal to 0. And I'm going to end up with x equals plus or minus 2. So I really have a grand total of 3 critical points. And so my number line would look, my sign chart would start to look something like this. And I would actually have to test each and every single interval because there's no trig function involved, and unfortunately we have no guarantee that the signs are going to change. But I'm going to stop right there tonight because I just wanted to show you not only do we set the derivative equal to 0, but we also have to set the denominator equal to 0 if that's the case and get more critical points. Alright, good luck tomorrow. We'll catch you then.